and that doesn't feel good. Okay, this is a demo that we didn't have in Montana, and we're gonna give it a try though. I'm gonna put some liquid nitrogen in this container,
Nice.
and then I'm going to screw this on the top. And then I'm gonna tap this off. Just all sorts of fun we can have. Now, I asked the demo folks to bring me over a racquetball. And you've all seen this demo before. You put the racquetball in there, it boils. Eventually, the racquetball gets to be the same temperature as liquid nitrogen, 320 below zero. And then you take out the racquetball and throw it on the ground and it shatters. That demo we can't do because unless this gentleman that had the extra battery has a racquetball in his backpack, is that one of those backpacks from Hogwarts that has everything? We can't do that demo. So instead of that, we're going to use my hand. So let me get this out of the way so everyone can see. Okay. Don't usually do this, but. Oh, what were you expecting? That's sick. That's fingers everywhere. Yeah, I can do that because of the boiling. When I put my hand in there, you saw the boiling happening. And that boiling creates a layer of gas around my hand that protects my hand from the cold. We call it the Leidenfrost effect. That's what you get when you buy a down jacket from REI. The goose down feathers are not what's keeping you warm. They just create a layer of air, of gas that protects you thermally from the cold. Now that only works for a while. If you leave your hand in there too long, then it's a different, that's biology. Okay, this Leidenfrost effect allows me to do this last demo, which is truly stupid. Oh, yes, I am. That demo has not always gone well. A grad student in New York was doing that and accidentally swallowed some of the liquid nitrogen. It started expanding and expanding just like it did in there. And he had to have many operations to repair the damage that was done. It hasn't always worked well for me either. I was invited to Helena, Montana. That's, for those of you that don't know, that's the capital. It's about the size of Springville. And anyway, I was invited up there to speak to the legislature. I'm way ahead of you, brother. Leave it anyway. Yeah. Oh, we've got a racquetball. Anyway, I was invited to speak to the legislature about what we were doing in the physics department with our teaching program. And as part of my demo, the governor and his entourage were right down front. I was very nervous. Part of my demo, my talk, I did this demo. And I was so nervous that, first of all, I spilled some liquid nitrogen and it collected there at my belt. That was when I was skinny. Anyway, I still have a scar there. The worst thing was I swallowed a little bit. And then for the rest of my talk, every time I tried to say anything, I would belch and smoke came out. And my talk was over. That was the end of it. And so we didn't get funded. So let's do the racquetball demo. Okay, so. Oh, man. I don't know if that's gonna break. Seems pretty sturdy. So. Austin, is that boiling? Would you say that's boiling? It is boiling, thank you. Verified. Now, when that stops boiling, the racquetball will be 320 degrees below zero. Now, right before it stops boiling, we get a crescendo. It just, oh. I'll tell you, oh, we can hear it. Oh. Maybe at the end of class, I'll get this thing out of here. At the end of class, if any of you want to stick your hand in here, I just ask that you not have any jewelry, that you pull up your sleeves so that you don't get any clothing wet with liquid nitrogen, because then it can stay against your skin and do damage. And be brief, don't linger in there. Okay, we're gonna break that at the end of class. So let's talk about collisions in 2D. And we have Zoom yet? Oh, thank you, Sam. We have an exam coming up next weekend, opening next Friday, a week from tomorrow. And as I promised you, that would be entirely multiple choice. And over at the testing center, there are 2 practice exams and their solutions at Max. I posted them yesterday. And we'll have a review session next Wednesday in this room at 7 o'clock. And I will record that and post it to YouTube as we normally do. That exam will cover energy and momentum. Now, last day we looked at this problem, and it's very, very, very similar, by which I mean the same as one of your homework problems. So let's work that problem. Sam, there was a piece of paper right there. You know. Oh, thank you. Okay. So we have this hand that is pushing a block with a force of 75 newtons per 2 meters. And that gets the block up to speed. And we find that after it goes across this rough patch, it's going at 8 meters per second. And we want to find the length of that rough section of table. Remember, the biggest decision that we always have is this an energy problem or is this a momentum problem? Tell your neighbor, which is it? Energy or momentum? Okay. I hope you all said energy. Remember our decision tree. We first asked, is this a collision? Well, it's going to be a collision in just a moment, but when it's at that point going 8 meters per second, the collision hasn't happened yet. And then I asked the second question, are we asked about time or do we need to use time? No, we're asked about distance. Distance is always energy. Remember, force times distance is the vec that changes energy. So I would start this with the grand high energy in the morning is equal to energy at night, except when it isn't. And it isn't when there's external, spelled with an X, external vec. So initially, if I look at right before we start pushing, let's call that point A. And we asked the same three questions. Is anything with mass moving? Not yet. Anything up off the floor? No. Any spring, stretch, or compressed? No. So I got nothing. And then I go to the end. That's going to be this point here, where it's going 8 meters per second. Let's call that point B. And I asked the same question. Anything with mass moving? Yeah. So I got 1/2 mv squared. Anything up off the floor? No. Any spring, stretch, or compressed? No. Now, 0 is not equal to that, so Werk was done. And indeed, there was 2 works done. There was the hand pushing with 75 newtons for a distance of 2 meters. And then there was negative Werk done by the friction force times that distance that we're looking for. Now, let's plug in some numbers here. This is going to be 0 plus 150 Newton meters. That's just another way of saying joules. The friction force, anytime I want a force, I draw a free body diagram. The weight of that block is going to be, the mass of that block is 3 kilograms, 30 newtons. Table on the block, 30 newtons. And we have a friction force that is the easy kind of friction, just the mu sub k times the normal force. That's going to be 0.3 times 30, and that's going to be 9 newtons. Okay. So I'm going to plug in 9 newtons here, multiply that by delta x, which I don't know. That's going to equal 1/2 times 3 kilograms times 8 meters per second. I got to square that. Remember to square that. And that's equal to 96 joules. Now it's just algebra. And when I solve for delta x, what I'm going to get is 54 joules over 9 newtons, and that's going to give me 6 meters. Okay, check on your neighbor. Your neighbor okay? Squared to block B or for okay. Oh. That's supposed to be point B, not point B.
That makes sense.
Okay. We're told in part B that right after the collision, block B is found to be moving to the right with a velocity of 4 meters per second. We want to know the velocity of block A, the 3 kilogram block. And we want to know both the magnitude, always a positive number, and the direction, which can be positive or negative in a one-dimensional problem. So is this energy or momentum? Shout it out.
That's it.
Yeah, it's a collision, so it's momentum. So we start always with a momentum problem. We start here, P initial is equal to P final. And because that's a vector equation, we need a coordinate system always. And so initially, right before the collision, that's what that means. I have the 3 kilogram block moving at 8 meters per second, and it's in the positive direction. I have the 7 kilogram block moving not at all. You see, I just wasted ink. Afterwards, we know that the 3 kilogram block is, well, we don't know. Maybe it's moving, maybe it's not. Let's find out. Let's make that a positive variable. But we do know that the 7 kilogram block is moving at 4 meters per second to the right. And so if we, now it's just algebra. If we solve this, we get 24 Franci is equal to 3 kilograms V final, plus 28 franci. If I subtract 28 franci from both sides, I get negative 4 franci is equal to 3 kilograms V final. And that gives me V final is equal to negative 4/3 meters per second, or 4/3 meters per second left. One or the other, but not negative 4/3 left. Now, we said that the kinetic energy of the system before the collision was 96 joules. Remember, we got that right here. If we calculate the kinetic energy after the collision, we have to go 1/2 times the 3 kilogram block times its speed right after, which would be 4/3 meters per second. I got to square that. And then I've got the 7 kilogram block moving at 4 meters per second. I got to square that. Folks, again, I'm an old man. I wish I didn't have to say this, but the most common mistake is to not do that square right there. Not hit the button. You'll write it on your page, but no one's reading your page, people. It's Scantron, okay? So when I work this out, what I get is a number that just rolls off the tongue, 58.67 joules. But what you'll notice is that it's not 96. If it were 96 after the collision, this would be an elastic collision. So it's not an elastic collision. Well, that leaves two options, either inelastic or maximally inelastic. Tell your neighbor how you know that it's not maximally inelastic. Okay. If it were maximally inelastic, the two blocks, the little one and the large one, would be stuck together. They would be moving together. And that means they would both be going with the same velocity, and they're not. One of them's going at 4 meters per second, and one of them's going the other direction at 4/3 meters per second. So it can't be maximally inelastic. It's not elastic. The only thing left is inelastic. And so that would be the answer. Okay, now to introduce this idea of two-dimensional collisions, we're going to use our imaginations. And if you don't have an imagination, borrow one from your neighbor. Imagine, if you will, that we are looking down on a hockey rink, and we have two regulation hockey pucks coming towards each other at the same speed, one going to the east and one going north. Now, these are almost regulation. They're the same mass and size as the regulation hockey pucks, but we've lined the outside with Velcro so that when they collide, they stick, and we have a maximally inelastic collision. Now, if these two collide and stick, what direction are they going to go off at? This is, let me get you started here. Get your clickers out. Okay. It's given in the problem. Okay, folks. This is not rocket science. Oh, wait, it is. Last call. I never get tired of that joke. Old people are easily amused. Oh, good job, people, good job. Okay, now, next question. Imagine that instead of two regulation hockey pucks, I have one that's a Mondo hockey puck. And they're both going the same speed, one east and one north. What direction is most likely for the outcome when they collide and stick? With your clicker, please.
Was that not? What did you pass earlier?
Yeah, which way?
Okay. Keep your clickers out. We're gonna do a couple more of these. Okay, B is the correct answer. Now, what if I have the regulation hockey pucks, but one is going slow, one's going faster? Which of those arrows is most likely with your clicker?
That didn't go up so fast.
Oh, it's not on here? Oh, it's not on here, but it's on the piece of paper I gave out.
They always do ways.
Okay. Last call.
Respect on those thoughts.
Okay, D is the correct answer. One last question. In this case, I have a regulation hockey puck going fast to the east and a Mondo hockey puck going slow to the north. Which is the direction of the final velocity after the collision and they stick together? With your clicker, please, one last time.
It's twice the size. We can't tell. Yeah. A mass and. I'm saying that like number.
Okay. That'll do. Okay, we said C. The correct answer, my friends, is A. Ah. Those of you that you were set up, weren't you? You fell right into the trap. Those of you that said C were using what's called a compensation argument. That, oh, this hockey puck has more speed, but it's got less mass. Sixes, okay? Let me give you another compensation argument. It turns out Sam, our friend here, is taller than I am. If we take the number in inches representing our height, Sam wins, okay, genetics. If, however, we take the number representing our weight in pounds, I win, if we can call that winning. Now, if we take my weight and multiply it by my height and do the same thing for Sam, are we likely to get the same number? No, we are not. We are not, okay? And so that's what I mean by a compensation argument. Now, what do we do when we have things that are collisions that happen in two dimensions? Well, we remember that this equation, conservation of momentum, is a vector equation. And that means it's true in both the x direction and the y direction. And so I essentially can solve these problems by solving two one-dimensional problems. Now, you remember back at the beginning of the semester, when we were studying one-dimensional motion problems, we studied it for a fair long time. And then all of a sudden, right before the exam, I spring this projectile motion on you. That seemed cruel, did it not? Yeah. But remember, I explained that those two-dimensional projectile motion problems were just two, count them two, one-dimensional problems. And the big key to solving those was separating out the X part of the problem from the Y part of the problem, because nature treats them differently. Well, we're going to find that that's the same thing here. Now, here's a sample problem that we're going to work. We have a car of mass 2,000 kilograms going 15 meters per second, about 30 miles an hour, and it's going east. We have a truck of 8,000 kilograms going very slowly at 5 meters per second at 37 degrees north of east, and they collide and lock bumpers, becoming a very ugly vehicle with 22 wheels. And the question we're asked in this problem is, what velocity do they have stuck together right after the collision? Don't wait for them to stop and call the police, okay? Right after the collision, what is that velocity? Now, folks, this is real world stuff. The way I got my job at Montana State University is that the guy that had the job was working for lawyers, and he would go to the courtroom and just use these principles of conservation of momentum to tell the judge who was speeding, you know, just based on the skid marks and what evidence was there. And he was making so much money working for the lawyers that he couldn't afford to teach anymore. And so I was very grateful to take his place. Now, on a more serious note, in 1995, a man by the name of Timothy McVeigh blew up a Ryder truck, rental truck, next to the Murrah Federal Building in Oklahoma City. And in that explosion, it destroyed a third of the building. Remember the numbers here. It killed 167 people, 19 of them children. 684 people were wounded. It was the deadliest homegrown terrorist attack that we've encountered in the United States. And they didn't know who did it for the longest time. They knew that it was a Ryder rental truck because they had parts of the truck everywhere. They also knew that the truck was parked next to the building. They had video surveillance that saw it just parked there, but they didn't know who rented the truck, where the truck came from, until they used this principle of conservation of momentum. They used the fact that before the explosion, and remember an explosion is a collision, before the explosion, the truck was parked. The momentum of that system was zero. And then after the collision, if you add up all the pieces and the momentum that those pieces had, if you add that up as vectors, it should add up to zero. Well, they did that. They went looking for all the pieces of the truck, and based on where they ended up, they could figure out how fast they were moving when the explosion happened, and they added up all that momentum. And it didn't add up to zero. Something was missing that direction. And so they went that direction and they found a part of the axle. It just happened to be a part of the axle that had the VIN code stamped on it. And that's the way they caught Timothy McVeigh, and he's still in prison. Okay. This is real life CSI sort of stuff. And that's because we don't have to make any wishy-washy assumptions. We don't have to assume frictionless tables or massless strings or anything like that. We don't have to ignore air resistance or friction. It's just conserved. It's just conserved. So let's solve this problem. Thank you, Sam. Okay. So the first thing we're going to do is we're going to look at the momentum of the car and the momentum of the truck. And so if I look at the momentum of the car, that's going to be mass, 2,000 times speed, 15 meters per second, and that's going to give me 30,000 Franci. If I do the same thing for the truck, if I take 8,000 times 5, I get a momentum for the truck of 40,000 Franci. Now, if I asked you for the total momentum of that system, the system comprised of both the car and the truck before the collision, what would you say? Talk to your neighbor. What would you say? What's the total momentum of that system?
They're not add vectors, like they're vectors, so. We need to find the X and the Y part. We already
Okay,
know for C, but so we gotta find the X part and Y part for the truck. And then-
if you said 70 Franci, slap yourself good. Yeah. You can't add this up like money. You can do that with energy, but not momentum. This is not 30,000 Franci. This is 30,000 Franci east. And this is not 40,000 Franci. It's 40,000 Franci at a direction 37 degrees north of east. The most important step in solving these problems is that right there. Drawing that vertical line that separates out the X part of the problem from the Y part of the problem, where I'm using a standard coordinate system. Now the car is easy. That's all in the positive X direction. 30,000 Franci and nothing in the Y direction. For the truck, we have to break it up into components. I've got an X part of that momentum and I've got a Y part of that momentum. This is 37 degrees. Now this is going to be 40,000 Franci times the cosine of 37 degrees. And it turns out that that is 32,000 Franci. And this is going to be 40,000 Franci times the sine of 37 degrees, and that's 24,000 Franci. And so if I put that over here, the X is 32,000 Franci in the positive X direction, the Y is positive 24,000 Franci. Now, if I add that together, the total, I get 62,000 in the X direction, 24,000 in the Y direction, both positive. So what does that look like? Well, I've got 62,000 Franci in the X direction. I've got 24,000 Franci in the Y direction. That's going to give me a vector that has magnitude square root of 62,000 squared plus 24,000 squared. And that equals 66,500 Franci. This direction is going to be the inverse tangent of the opposite side over the adjacent side. And that's going to give me 21 degrees. So I would say, if I was asked for the vector of the total momentum of the system, I would say P total is equal to 66,500 Franci at 21 degrees north of east. Now, is that the total momentum of this system before the collision or after the collision?
Well, no, it's at.
Yes, both. That's the whole idea. The momentum of the system is conserved, stays the same. Now, here's the thing. After the collision, you can see it. You can see these two locked together, moving across the pavement in a direction of 21 degrees north of east. They're sliding, okay? If I know the coefficient of kinetic friction, I can even tell you how far they slide before they stop. But before the collision, the total momentum of the system is traveling in a direction 21 degrees north of east. But there's nothing that you can see with your eyeball traveling at 21 degrees north of east. There is something that you can't see with your eyeball that you're going to talk about in this week's tutorial, and that's called the center of mass. And that center of mass is going to move at the same speed in the same direction both before the collision and after the collision. And by that I mean right before the collision and right after the collision. It's just that you can't see that. It's a mathematical construct before the collision. Afterwards, because everything's moving together, you can see it. Okay, now we're not done with this yet. We weren't asked for the final momentum of this system. We were asked for the final velocity of this system. Now, in the case where everything's moving together, I know that the total momentum, if they're all moving together, I can treat them all as one thing. And so that means that the mass of the object would just be the total mass, and the velocity would be the final velocity of both the truck and the car, because again, they're moving together. And so this would be 66,500 Franci at 21 degrees north of east. And that's equal, the total mass is going to be 10,000 kilograms times the final. I made it 10,000 because I can divide by 10,000, okay? And so that's going to give me a V final of 6.65 meters per second at 21 degrees north of east. See if your neighbor followed that solution to that problem. See if your neighbor's on the bus.
Yeah. Do a cargo.
Not that
And then you just down whatever that angle.
Okay, if I might just speak comfort to your soul for a moment. That problem is more messy than anything I would put on an exam, okay? But I give it to you essentially so that to give you confidence. If you can see what I did there and follow what I did there, you're in good shape. You're in good shape, okay? Are there questions on that problem before we go to another one that's more likely to be representative of what you'll get on your exams? Okay. Sam, could you help me erase that board? I'll do this side over here. In this problem, we're going to pretend that you're working for the lawyer. Okay, I'm gonna leave this part here.
Pretty well.
Okay, so this will be, we are going to pretend that you're working for the lawyer and that you go to the scene of this collision. It was a maximally inelastic collision. They locked bumpers and they slid across the pavement. Now, judging from the length of the skid marks and the measured coefficient of kinetic friction, you figure out that after the collision, right after the collision, they had to be traveling at 20 meters per second. And the judge needs to know who to give the ticket to. And what you know is that in this neighborhood, this is a residential neighborhood, the speed limit is 30 meters per second, 60 miles an hour. It's a fast neighborhood. They don't love their kids that much. Now, that seems funny, but when you're going to Helena, Montana from Bozeman, you have to go through this little tiny town outside of Townsend. And right there on the side of the road, there's this little white schoolhouse. It's just the classic American, what it used to be when we were all living on the prairie. And right in front of the schoolhouse, there's a sign that says school speed limit 55 miles. It just, those kids are fast. They can get across that really fast. So this is a problem where we don't know what the initial velocities are. But we do know that car A is going all in the X direction. And so its momentum would be 600 kilograms times the A in the positive X direction and nothing in the Y direction. Car B, on the other hand, has all of its momentum in the Y direction, and it would be 400 kilograms times VB. I also know that right after the collision, that I have a total mass of 1,000 kilograms moving in a direction 53 degrees, spelled with a 5, at 20 meters per second. Now, that's going to give me 20,000 Franci. Now, that's my P final total. But it's also my P initial total. Okay, it stays the same. That's what conservation means. Now, in order to put that into my table here for P total, I have to break that 20,000 Franci up into its parts. Well, this is going to be 12,000 Franci, and this is going to be 16,000 Franci. Tell your neighbor how I got those numbers. Tell your neighbor how I got those numbers.
Never really understood that.
Okay, there's two ways. The first way you could recognize is that 53 degrees is a 3, 4, 5 triangle. And this is 5 times 4,000. So this must be 3 times 4,000 and 4 times 4,000. I could also say that this is equal to 20,000 Franci times the sine of 53 degrees. And this is 20,000 Franci times the cosine of 53 degrees. I hope you're bored with that because we've been doing that same trig problem the entire semester, okay? So I can put these in over here. There's a positive 12,000 Franci and a positive 16,000 Franci. And then I just add up both columns. And what I get is that 600 kilograms times VA is equal to 12,000 Franci, or VA is equal to 20 meters per second. They do not get a ticket. If I add up the Y column, I add up 400 kilograms times VB is equal to 16,000 Franci. And that means VB is equal to 40 meters per second, 80 miles an hour, reckless endangerment. Okay. That seemed like a doable problem, something that you could crush on an exam if your career as a doctor depended on it. And it does. Okay. You laugh now. The MCAT won't be so funny, will it? Okay. Let's try this one straight out of your homework. Okay, this is homework that's due next Tuesday, homework number 16. In this problem, 3 kids find themselves stranded on a frozen pond of frictionless ice. They try to get off the pond, but they scoot their feet and nothing happens. It's frictionless. Okay. So they come up with a great idea. They're standing next to each other. So they put their hands together and they say 1, 2, 3, push. And we find that child 1 takes off to the north at 4 meters per second. Child 2 takes off to the east at 5 meters per second. And we want to know the velocity, both magnitude and direction, of child 3. Now, you'll recognize this very much as the same problem as the Ryder truck exploding. Before they push, they're just standing there. The total momentum of that system is 0. And so after the push, after the collision, the explosion, the total momentum has to also add up to 0. Now, folks, many of these homework problems, most of these homework problems, are old exam problems. And when this was on an exam, it was a tragedy. Because what I saw over and over again as I was grading the exam was that students said, well, student 1 was going off at 4 meters per second to the north. Student 2 was going off to the east at 5 meters per second. And so that means that student 3 had to cancel out this velocity and cancel out that velocity. And so this is going to be the square root of 5 squared plus 4 squared. Wrong or sick and wrong? Tell your neighbor why. What is the mistake there? What is the mistake there?
Can't forget about the mass.
Yeah, I definitely.
Okay, I hope what you told your neighbor was that there's no such thing as conservation of velocity. There's conservation of momentum, not velocity. What tripped up my students was that I asked them for the final velocity. And so they immediately started using the velocity. But there's no there, okay? That's not what's important, not the velocity, but the momentum. Now, I know that the momentum of child one is going to be the mass of child one times the velocity of child one, and that's going to be 200 Franci. And if I look at child two, the momentum is going to be the mass 30 kilograms times the velocity of 5 meters per second. So that's going to be 150 Franci. Okay. Now, before we go to the answer, there was another part to this problem when it was on the exam and in your homework. And that is, you were asked to compare the impulse on student one to the impulse on student two. Which one experiences the greater impulse? Tell your neighbor what the answer is there. Which one experiences the greater impulse during this explosion? Well, so the funny thing is, on the exam, many of the students threw my words back at me. They said, oh, ho, ho, Greg, you can't fool us. You taught us that during a collision, which is an explosion, the total impulse is zero. So it's zero. Zero for child one, zero for child two, zero, zero. No, that's not what I taught you. I taught you that if you include everything in the system that collides or pushes or explodes against each other, the impulse on that system will be zero. But the impulse on child one is not zero. Let's see what it is. If I look at child one, and I use P initial plus the impulse is equal to P final, she was just standing there, and then an impulse happened on her. We'll call that impulse on one. And afterwards, she had 200 Franci north. Well, the impulse on her was 200 Franci north. And if I knew the time involved, I could figure out the force on her, but we don't. I just know the impulse, which is the combination, the product of the force times the time. If I look at child two, well, there she starts with zero momentum, and then there's an impulse on child two, and then finally she has 150 Franci east. Okay, so there's a bigger impulse on child one than on child two. So I'm going to need to redraw this picture a little bit. The total momentum has to be zero. So child three has to have 150 Franci to the west to cancel that out. And 200 Franci south to cancel that out. And so that's going to give me a momentum of 3 after the collision of 250 Franci. I got that because this is 3 times 50, 4 times 50, 5 times 50. That makes this 53 degrees south of west. Now, again, we didn't want the momentum. We wanted the velocity of child three. Well, the momentum of child three is just the mass of child three times the velocity final of child three. So that means 250 Franci at 53 degrees south of west is equal to her mass. Her mass is given as 50 kilograms times V final of 3. And that gives me V final of 3. 250 divided by 50 is 5 meters per second at an angle of 53 degrees south of west. Again, see if your neighbor is equipped to solve a problem like that on the exam, because this is the type of question that shows up on an exam. Sam?
But I got.
Thank you so much. Thank you so much. Can I get one of them?
You get out multiple. He's giving me full silver.
Okay, we are going to, we're going to look in the last 10 minutes, we are going to look at one more problem. This problem is on the back of this exam preparation sheet. The exam preparation sheet tells you about the exam, where to go, where the review session will be, what skills you should have in your toolbox to prepare you for the exam. In this problem, we have a 250 kilogram asteroid traveling to the right there. And then suddenly it just explodes into 3 fragments. And we're given some information about those fragments. For fragment 2, we have a lot of information. We've got its mass, we've got its velocity. For fragment 3, not so much. We know its mass, but we don't know its speed. We do know its direction. It's going 37 degrees below the horizontal. And for fragment 3, we just know the mass and the direction, which is to the left. And we're asked some questions about that. The first thing we're asked is to find the X and Y components of the asteroid's momentum before the collision. Now, that's pretty easy because the asteroid's the only thing in the universe that's moving. It's just all by its onesies. It hasn't become fragments yet. And so I just take the mass of that asteroid and multiply it by the velocity of the asteroid. And there it is. And that's going to give me 3 times 250 is 750 Franci in the X direction and nothing in the Y direction. And that's P total both before and after the collision. Before and after the collision. Now, if I look at those three fragments. We're asked about the kinetic energy before the collision. That's pretty easy. That's just 1/2 times the mass times the speed squared. That's not really a big part of the problem. Okay. Find the X and Y components of fragment 2 with your neighbor real quick.
I figured you wouldn't have made that. And she's like.
Yeah, I think, sure, I got it. Okay.
Okay. So if I look at the momentum of fragment 2, it's 5 meters per second times 120 kilograms. That is going to be 600 Franci. Did I do that right? Okay. Now I need to break that up into parts. And that's going to be 360 Franci and 480 Franci. Okay, and this is 53 degrees. Now, again, that's a 3, 4, 5 triangle, 3 times 120, 4 times 120, 5 times 120. Or you could do it the other way. So I'm going to put that in here. I'm going to put in plus 360 plus 480. Now we're asked about fragment 2, and this is where we have to be creative. We know 2 things. We know that the momentum of 2, I'm sorry, I misspoke. We're looking now for fragment 3, not 2. We have 2, that's this one. And we put it in the wrong place. Why did not anyone speak up? We're just gonna let the old man just wander around aimlessly, you know? If I start to drool, are you gonna do something? I mean, is somebody gonna call authority? I was counting on you people. Okay, now we're back on track here. Sam, you could have helped too. We know that this momentum travels at 37 degrees below the horizontal. But we also know that the momentum of fragment 1 is all in the X direction. There's nothing in the Y direction. And I can write the momentum of fragment 1. It's in the negative direction. It's 50 kilograms times VA. Now, is VA going to be a positive number or a negative number? Well, positive. I've already put the minus sign here. VA is not the velocity of A, it's the speed of A, the magnitude. What's on the speedometer, okay? The important thing is none of it's in the Y direction. And this column has to add up to 0. So that means that fragment 3 has to have negative 480 Franci in the Y direction. Does everyone see that? Got to add up to 0. So I know that when I break this up into components, this has to be 480. Now, there are several ways I can find this. This is going to be 640. I know that this is 3 times 160, and this is 4 times 160. And this is going to be 5 times 160 or 800 Transite. I can also say that Py over Px is equal to the tangent of 37 degrees and solve it that way. So if I come over here and put in 640, I get my answer to part D. Now, the last part of this problem, and we've got 3 minutes left, is what speed does fragment 1 have? And again, remember, VA is a positive number there. It's a speed. Well, we've already used column Y. Let's use column X. If I add up everything in column X, I've got minus 50 kilograms VA plus 360 plus 640 has to equal 750. That's the total, both before and after. Well, that's negative 50 kilograms times VA plus 1,000 spelled with a 1 is equal to 750. And that means negative 50 kilograms VA is equal to, if I divide, subtract 1,000 from both sides, negative 250. And that gives me VA is equal to 5 meters per second. I already know it's to the left. I looked at the picture, okay? Folks, I hope that was enough of a practice that your homework and ultimately the third exam is a piece of cake. Yes, you will have to understand Galilean transformations for the exam. Yeah. Oh, we've got a racquetball, folks. We've got a racquetball. Let's break it.
Let's try it.
Hit it with a hammer.
Ah, okay. Did anyone get hurt? Okay, we're all good. If you want to put your hand in here, be quick about it. Don't be lingering.